Before plunging into finding Fourier series for other functions, let's introduce the following useful concept. A function f is odd if f of x equals minus f of minus x for all x, and even if f of x equals f of minus x. The term even and odd come from our fundamental even and odd functions, which are f of x equals x squared, which has f of x equals f of minus x, and f of x equals x to the third, which has f of x equal minus f of minus x. And so our fundamental even function has an even exponent, and our fundamental odd function has an odd exponent. So let's determine whether f of x equals cosine of 5x is even or odd, and we observe that f of x equals cosine of 5x. F of minus x is, which simplifies to, and so f of x equals f of minus x for all x, and so f of x equals cosine 5x is an even function. It can be difficult to identify odd and even functions algebraically, but if we graph y equals f of x, then if f is odd, then f of minus x equals minus f of x. But if xy is a point on the graph, we know that y equals f of x, and so f of minus x equals minus y. And so minus x minus y is also a point on the graph. And so for an odd function, if xy is on the graph, so is minus x minus y, and this means the graph is symmetric about the origin. On the other hand, if f is even, then f of minus x equals f of x, and again, if xy is a point on the graph, we know that y equals f of x, and so f of minus x equals y, so minus xy is also a point on the graph. And so for an even function, if xy is on the graph, so is minus xy, and this means the graph is symmetric about the y-axis. So what's the big deal about even and odd functions? Since the sum of odd functions is odd, and the sum of even functions is even, we have the following theorem. If f is an odd function, the Fourier series will consist of sine terms only, and if f is an even function, the Fourier series will consist of cosine terms only. So let's try to find the Fourier series for this function, which might seem a little daunting in its description, but note that this function is equivalent to the following. If k is 0, then we're 1 between 0 and pi. And again, if k is 0, then we're minus 1 between pi and 2 pi. If k is 1, then we're 1 between 2 pi and 3 pi. And again, if k is equal to 1, then we'll be minus 1 between 3 pi and 4 pi. And this behavior continues ad infinitum, and so our graph is going to look like this. And if we look at the graph, we see that our function is an odd function with a fundamental period of 2 pi. And so we know the Fourier series consists of sine terms only. So assuming our function is a trigonometric series in sine only, we make the following observations. If n is equal to 0, sine of 0x is 0, so there is no b0 term, and our series can actually begin at 1. And remember, if it's not written down, it didn't happen, so we'll make a note of that. And so we say that we find f of x equals a series in sine from 1 to infinity, where we don't yet know what the coefficients are. So let's figure those out. So remember, don't memorize formulas, understand concepts. Once we've assumed that our function has the form of a trigonometric series, remember that we can find the coefficients through integration. So we'll multiply our series by sine of kx and integrate. Assuming convergence allows us to interchange the summation and the integration. And the important idea here is that for n not equal to k, the integrals will evaluate to 0, leaving as our sole survivor the integral with sine kx. And this will be bk times pi. And so for k greater than 0, bk will be 1 over pi times the integral from 0 to 2 pi f of x sine of kx. Now to evaluate this integral, we'll need to remember what our function is, and the important thing to recognize here is that the function value changes at pi. And so we split this integral to the part between 0 and pi, and the part between pi and 2 pi. Between 0 and pi, the function value is 1. Between pi and 2 pi, our function value is minus 1. So we'll evaluate each of these integrals. And it's worth noting that for any value of k, cosine of 2k pi is going to equal 1. And so we can simplify our expression a little bit. Again, if it's not written down, it didn't happen. So we make a note that our coefficients of the Fourier series are going to have the form 1 over pi times 2 over k minus 2 cosine k pi over k. Now, while we could leave this in this form, we're not going to because we can do a little bit more simplification. And that emerges as follows. The value of cosine k pi depends on k. If k is even, cosine of k pi is equal to 1. If k is odd, cosine of k pi is equal to negative 1. So if k is even, our expression for bk will become 0. But if k is odd, our expression for k pi will be 4 over k pi. And so our series will look like, and if you want to show off a bit, you can rewrite our series in this form. And if possible, it's always a good idea to graph your series just to make sure it looks something like the function. So we have our original step function. If we graph the function equal to just the first term of the series, it looks like this. If we include the first two terms of the series, we get. If we include the first three terms of the series, we get. And it's certainly looking like our trigonometric series is going to converge to the step function.